So here I'm just going to show you a few examples of actually how to prove things in geometry. So our given statement is that L is parallel to M, and that actually can't be assumed until we're either given that or we have those little arrows that actually imply that. But that is going to be the start of our proof. Line L is parallel to line M, and that is how we start every single proof, by starting with the given statement. We want to end with this provable statement. So we want to get to angle 2 is congruent to angle 7. And really, in our list of definitions that we have over here that we've actually already established, we have that as alternate exterior angles. But I just want to show you how we get there, even with something that is, really, this should actually be kind of a theorem because it's a provable statement, not an assumed true statement. But for us, we're using it as a definition or postulate where we can use it as a logic to prove something else. I just want to show you how we can get to that as a hard and fast true statement. So we want to prove that that is congruent to that using another set of logics in here. So first, I kind of want to just think about how I actually am going to prove that, and then start listing out the statements and reasons. And there's a few different ways that you could do it. I'm seeing that angle 2 and angle 6 are corresponding angles. If I know that these are parallel and these are corresponding angles, then those have to be congruent. And then 6 and 7 are vertical angles. So if those are congruent and these are congruent, then I know that 2 and 7 are congruent. So I'm actually just going to list out those statements first. So I know angle 2 is congruent to angle 6. And I know angle 6, oops, that's a G, is congruent to angle 7. Therefore, I know that that's actually congruent also. I know that angle 2 is congruent to angle 7. And now I want to think about the reasons that I can actually use to justify that. Well, angle 2 and 6 are congruent because of the corresponding angles postulate. Which says that if these two lines are parallel, which was established by that first given statement, then these corresponding angles are congruent. Now 6 and 7, those are congruent really just by the definition of vertical angles. And then actually we're going to use a property that's not really on here. It's one of our algebraic properties, but the transitive property allows us to say that if A and B are equal, B and C are equal, then we can skip right over B and say that A and C are equal. So by the transitive property. So we have to justify each of those steps with either a property, definition, theorem, or a postulate that we already have established. So here I have QVW and RWV. Are supplementary, and I want to caution you here not to change the given statement at all. I know what you can conclude based off of that these are going to add up to 180, but that's not what it's saying. It's just telling you that they are supplementary. That is the given statement. So let's think about what we actually want to prove. QVP, we want to prove that that is congruent to RWV. We want to prove that those two corresponding angles are congruent. So I know I could be using corresponding angles here. If I know that these are parallel, then I could be using that. But I don't really know that yet. All I know is that these two are supplementary. That one and that one are supplementary angles. So I'm actually going to start with that as my first statement, that angles QVW and RWV add up to 180 degrees by the definition of supplementary angles. So from there, I'm thinking, well, if those add up to 180 and these two also add up to 180, QVW plus QVP That's again by the definition of, I'm going to actually call that linear pair. Wow, I'm just messing that up all over the place, but linear pairs. You could also say supplementary, but I just see that as on the same line, so they're also a linear pair, and it's just a little bit more concrete there. So by the definition of linear pairs, I also know that those two add up to 180. And now I can use the substitution property, which is a property of algebra. And that says if two things are equal, they could be substituted into the same equation. So I say that this equals 180 and this equals 180. So actually, I'm going to think about taking this whole thing and putting it in place of that 180. So I'm going to write this real small. QVW plus RWV equals that. QVW plus QVP. And now, since I have the same thing on both sides, I can subtract that away. I can take away the measure of angle QVW and QVW on that side and that side. So I'm going to call that SPO, the subtraction property of equality, which will leave me with RWV as congruent to QVP. And that is what I wanted to prove. I guess actually I should be thinking about the symmetric property from there, that I really have to flip this around. Let's just be exhaustive here, but I'm going to call that the symmetric property. And say that if this is congruent to that, then I can actually also flip this around and say that angle QVP is congruent to RWV. I'm going to prove this in a completely different way now. So I'm going to erase everything here and start with the exact same given statement. And this is really just to show you that you can do this in a lot of different ways. That one was more algebraic, the way I kind of set that up as two different equations and then solve the equations. This next one I'm going to use more of geometry logic and that language of logic that we talked about in our very last video. So really, I'm going to think about how I can prove that these two lines are parallel. If I know that these two, the red ones, are supplementary, well, those are consecutive interior angles. But the problem is the consecutive interior angles actually works the complete opposite way. It's assuming that if these two lines are parallel, then these two are supplementary. I'm given the second statement there. I'm given the conclusion, and I want to work backwards to the hypothesis. So I really want to use the converse of that. I want to flip that around and say that the converse is true. The converse of the consecutive interior angles postulate is true, because this is an if and only if statement. That statement works forwards and backwards, so I'm using it backwards. I'm using the converse of that postulate right now. So that is telling me that those two lines are parallel. Let's call those lines UV and TR, although you can name them differently. But by the converse, by the opposite of that statement, I can conclude that those two lines are parallel. Then from there, I actually can already assume that my proven statement is true, because these two angles are corresponding angles in a set of parallel lines. So by the corresponding angles postulate, I can jump right to my proven statement, my eventually proven statement.